Welcome to today's MeKo MedTech Materials webinar about developing nickel-free implants for allergic patients. My name is Laura Denzer. I'm one of the project managers at MeKo, and together with our CEO, Clemens Meyer-Kobbe, we form the speaker team today. After some practical information, we will start with the content. The webinar will take about 30 to 45 minutes, and the recorded video and the slides will be available on our website later on. For any questions that might arise during the webinar, please send us your questions and write them down in the question area. We're going to answer all questions at the end of the webinar or in personal messages afterwards. You will find the question area on the upper right screen side as shown here. And Q&A might also be named different in your language. For example, in German, it is called F&A. Let's have a look at today's agenda. First, I will give you a short overview of our company and the production of medical components. Then Clemens Meyer-Kobbe will focus on our principal topic, the material Vasculoy, and how easily you can change your medical devices to nickel-free implants. At the end, as I already mentioned, we will have a Q&A period to answer your questions written down in the questions area. All right, so let's start. For the next 5 minutes, I will give you a general overview of MeKo MedTech. Here you can see some pictures of the very beginning of MeKo. Clemens Meyer-Kobbe started the company in a garage as a one-man job shop in 1991. This is also the place where the stent manufacturing started, with laser cutting the first stainless steel stents in 1995 without actually even knowing that it was a stent. A few years later, stents made out of nitinol also joined our production portfolio, so that the company moved to its current place in 1997 and evolved to a quite big complex over the past 25 years. The last expansion is the part in the front where most of our production departments for nitinol components are located. And we also bought the building on the right side last year so that we could expand our production capacities. The planning for the next building is also ongoing so that we will have even more production capacity in the near future. Today, we have more than 300 qualified employees who are dedicated to high precision in the laser material processing and also the associated post-processes. Some of you might already know about this. Our company is ISO 13485 certified and intends to also obtain the ISO 9001 certification later this year. We are a globally active company. Most of our exports go outside of Europe to countries in the rest of the world. But now you may be wondering what actually happens in the background after we receive a request for a component from you. Let's have a look at the process. Naturally, every component starts with some kind of raw material. That's why MeKo, over the 30 years of its existence, has continuously built up a very substantial material stock. We have at the moment more than 3,000 different material lots on stock. So for most prototypes, we can find some raw material in-house directly. Obviously, the list starts with the established cobalt, chromium, and stainless steel stent materials, but also includes nitinol and different bioresorbables like our magnesium alloy Vasculoy and our polymer tubing polymedics. Vasculoy is the alternative material specially developed for nickel-free stents. To secure the quality of all this material we use here in-house, we perform an inspection of all incoming material. Let's go through the general production process, which actually most of our devices follow. The first step is the laser cutting. We also offer laser drilling and laser welding. And for all these processes, we have an in-process quality control, which allows us to achieve a superior dimensional accuracy. As a following step, we are able to heat treat or shape set your medical device. And of course, it depends on the material which process we would apply. A lot of medical devices need to be electropolished afterwards, and our machines allow us a widely adjustable range of material removal. For the subsequent passivation, we use an automated cleaning line to reach consistent results and to enhance the biocompatibility of the components. Finally, each part needs to pass our quality control, and for medical devices, we perform a 100% visual inspection and own several different automatic microscopes for further controls. In overall, with our comprehensive material experience and usage of serial production machines for both prototypes and serial production, we provide full flexibility for your device. A 24/7 manufacturing and a rapid production option even enhance this flexibility. In the end, I should also not neglect our R&D department. It might actually be a bit unusual for companies like ours, but we are quite broadly positioned and also have been researching in the field of materials sciences for about 15 years now. We offer our own resorbable material, Polymedics, a polymer, and Vasculoy, a magnesium material, but as well Vasculoy, our nickel and cobalt-free material for stents, which Clemens Meyer-Kobbe is going to present now. Before he starts his presentation, I just want to remind you of the Q&A area. Please let us know your questions and write them down there.
So here I'm taking over. Thank you, Laura, for the introduction. Dear webinar guest, the first part of my talk is more medical related and the second more technical. First of all, I will talk about the relevance of the nickel allergy. Is the nickel allergy just a dermatitis problem, or could it harm the whole body? Do we really need a nickel-free alloy? This is the first question. If yes, what are the material requirements for a nickel-free alloy, which will be used for stents? With this information, I will give you a general introduction to Vasculoy, the nickel-free alloy. In the next chapter, I will discuss the material properties of Vasculoy. With the material properties in mind, the question comes up how Vasculoy is evaluated in comparison to other stent materials. Finally, I will explain the roadmap for the development and registration of a Vasculoy stent. So, the main question is, do we really need a nickel-free alloy? What are the constraints? In general, studies show that approximately 13% of the population are allergic to nickel, with a strong upward trend. The number of 13% varies a bit from study to study, but in general, more than 10% have a nickel allergy. Very often a light allergy, not very strong. It is known that women show a higher incidence of nickel allergy. It is assumed that they develop the nickel allergy due to their earrings, but also piercings. Typically, we only see the skin. It means the dermatitis reactions on nickel. But what happens in the body? Here, studies show that individuals who are allergic to nickel demonstrate a greater restenosis rate. It is difficult to trace the restenosis rates to a certain root cause, but in comparison of patients with and without nickel allergy, the patients with a strong nickel allergy show a higher restenosis rate. There's also a study on the level of cells, which investigated the reaction of cells to nickel contents. The study proves that the corrosion products of stainless steel, the 316L, are toxic for primary cell cultures. Out of the group of patients with nickel allergy, so the group of about 13% with nickel allergy, a few patients show a severe allergy. In the picture shown as the man in red. These patients with a severe nickel allergy are seldom, but show immediately significant symptoms after a stent implantation. Two samples are shown in the next slides. A middle-aged man, a worker in a factory, was suffering from claudication in his right leg. Finally, he received a nickel titanium stent in his superficial femoral artery, so the upper leg. After a few days, a rash started in his right lower leg, below the knee. You see it here. This shows that the reaction on a nickel allergy is not always exactly at the location of the implantation. Over the time, the rash went worse. The leg showed strong dermatitis. Finally, after 8 months of different unsuccessful medication, the nickel titanium stent was explanted, exchanged against a siphonos vein graft. Already 1 day after the operation, the itch was gone, and after 1 month, the patient was free of allergy symptoms. And there's the next sample. A Japanese woman received a stainless steel 316L stent. It was in the iliac position here. It was an express iliac stent from Boston Scientific. I announced the name of the company, not to blame the company, but to prove that the stent is a regular stent from a well-respected company. Shortly after stenting, a band-like erythema was observed around her navel, which worsened over the time into a general rash around her body. Searching for the reason of the rash, finally patch test proved her strong nickel allergy. Again, no medication really helped. The only relief was the explantation of the iliac stent. After the explantation, her dermatitis significantly improved and her depression disappeared immediately. At MeKo, we also made our experiences with nickel allergy due to 2 employees with a strong nickel allergy. One young man was deburring nickel titanium stents. Immediately, his hands were swollen and pure red. No chance. He had to quit his job. In another case, a young woman who was electropolishing stents exhibited nickel allergy symptoms. In the beginning, we protected her with hand gloves, but the symptoms returned. So we packed her more and more with protective wear, but the nickel allergy developed even stronger. Finally, she had to quit her job as well. This shows, as we all know, that a simple allergy with only minor symptoms can develop to a strong allergy with severe problems. These 2 cases of our employees with severe nickel allergy triggered and encouraged us to develop a nickel-free alloy suitable for stents. Before I leave this medical part of my presentation, I want to resume. We know that a nickel allergy can be developed over the living age, or a light allergy can become stronger over the years. Patients with a severe nickel allergy should be careful with nickel-containing implants, or should be completely excluded from nickel-containing implants. The problematic of nickel allergy is well recognized by the national authorities. Regulatory requirements and restrictions regarding the nickel content of devices for human bodies are shown in this slide. First, there is the European Parliament and Council, which passed a nickel directive to limit the nickel content in products used for epithelialization to 0.5 per mil mass to nickel to total mass. This is 500 parts per million. This directive also limits the nickel release from objects intended for use in direct and prolonged contact with skin to 0.5 microgram per square centimeter per week. Also, the FDA is concerned about devices with nickel content and therefore released 2 information. One is the biological responses to metal implants. and the other is called the guidance corrosion on implant devices made of nickel-rich alloys, which may lead to various modes of toxicity. If there are these legal or governmental requirements and restrictions, the following questions arise. Who takes the responsibility for implanting a nickel-containing device if an identical nickel-free device is available? And can nickel-allergic patients claim for indemnification if they experience restenosis, especially if an alternative product, so an alternative stent without nickel, is available? The consequence is, as we see it at MeKo, that patients have to be tested for nickel allergy before implantation of a nickel-containing implant, not only for stents, but in general for any metal implant. So far, patch tests are the way to test the nickel allergy. If, as we now learned, nickel-free stents are necessary, what are the material requirements for stents? Now the next part of my talk becomes more technical. There are 5 main characteristics a stent material has to fulfill. We have the mechanical properties with the strength and the strain, which means plasticity of the device. We have the corrosion resistance, the biocompatibility, the MRI compatibility. MRI means magnetic resonance imaging, and the radiopacity. And these are the requirements. With the mechanical properties, we want to ensure thin strut sizes, and the stent should be highly deformable without cracks. Corrosion resistance. This means we don't want any degradation or ion releases. We also don't want negative tissue reactions, which can only be ensured for all patients if the material is nickel-free. And we don't want artifacts under the magnetic resonance imaging. And finally, the cardiologists, they want to have a good visibility on the angiographic or under X-ray. When we were developing the nickel-free alloy, we had to pay attention to these 5 characteristics. Finally, we succeeded to develop a suitable nickel-free alloy and called the material Vasculoy. First of all, why we call the material Vasculoy? It's quite simple. As the alloy was especially developed for vascular implants, we combined the 2 words vascular and alloy to Vasculoy. In principle, there are many nickel-free industrial alloys, which are nickel-free. But industrial alloys are developed for high strength. Plasticity is not necessary. No one wants, for example, a screw which can be elongated by 50%. But stents need this plasticity. We call it break elongation. For example, coronary stents are crimped down to less than 1 millimeter and expanded in the human body to more than 3 millimeter. During this high deformation, the stent struts should not break. Therefore, we need the plasticity. All implant materials like stainless steel, which is 316L, and the cobalt chrome alloys L605 and MP35N, or the platinum chromium alloy or nickel titanium, have a significant portion of nickel in the alloy. So all stents which are recently on the market have a significant portion of nickel. The nickel content, for example, in stainless steel, improves the stability against corrosion. And therefore, also for the other alloys, nickel is an important component in the alloy. It is well known that nickel can be replaced by nitrogen. First, this sounds very strange, as nitrogen is a gas. How to get it in a metal alloy? This is possible during the melting process of the alloy under high pressure of nitrogen atmosphere. Nitrogen takes over the responsibility of nickel. So nitrogen stabilizes the austenite grain structure of the alloy. And austenite grain is non-magnetic and corrosion resistant, two properties we need for stents. Nitrogen has also a strong effect on the mechanical properties of an alloy. The higher the nitrogen content, the higher the strength, but also the brittleness, which we don't want in stents. In our investigations, we had to look for the right alloy and the best nitrogen content to achieve the optimum material properties. And we have to keep the nitrogen content in a small concentration range to preserve the good properties of Vasculoy. The following slides, I will discuss the material properties of Vasculoy in comparison to other stent materials. First, everyone is looking for thin stent struts and a high deformability of the stent. That means we have to look to the strength and strain of the material. The strength and the strain are tested in tensile machines, where the material, here the stent tubes, are clamped and elongated with high forces. The elongation is plotted against the forces, respectively the stress. The diagram on the left side shows the stress-strain curves. On the y-axis, you see the stress, and on the x-axis, the strain. You see three curves: stainless steel, so 316L, this is the blue one, L605 and Vasculoy. 316L has the lowest strength and is with only about 650 megapascal of strength without cracks. Also, the maximum strain is limited to about 50%. That means the tube can be elongated by 50% before it breaks. L605 and Vasculoy have much higher mechanical properties. Nowadays, L605 is a typical material for coronary stents. Nearly all coronary stents are made of L605. L605, here the red line, has a high strength of slightly above 1000 megapascal and a very high break elongation of nearly 70%. When we developed Vasculoy, we tried to mimic the mechanical properties of L605 as good as possible. Vasculoy has about the same strength like L605, only a bit less than 1000 megapascal. And the break elongation is the same. With a higher nitrogen content, we would be able to achieve much higher strengths for Vasculoy, but then we are losing the plasticity. That means a high break elongation. So the take-home message for this slide is Vasculoy has a high strength and break elongation nearly identical to L605, which is the standard material for coronary stents. The material properties shown in the last slide, so the strain-stress curve, define also the recoil of the stent. The recoil is the value of elastic retraction. After the balloon expansion of the stent, the balloon is deflated, so the pressure is reduced and the stent reduces slightly its diameter due to the material elasticity. The diameter reduction is called recoil. To compare the three materials, 316L, L605, and Vasculoy in real-world circumstances, MeKo manufactured stents out of these three materials with identical design, so the same geometry, strut properties, etc. These identical stents, only different in material, were tested for recoil. Table shows that this is recoil, that 316L has the lowest strength and therefore lowest yield strength. That means it starts to deform at lower forces. So it has the lowest recoil. Vasculoy and L605 have similar but slightly bigger recoil values. This was also anticipated as the mechanical properties are very similar, if you remember the stress curves of the last slide. So the take-home message is Vasculoy has nearly or has an equivalent recoil like L605. Corrosion resistant is important to avoid any release of heavy metal ions. The corrosion resistant is measured by a cyclic potentiodynamic analysis according to the ASTM standard F2129. The explanation of the graph on the left side of the slide is difficult to explain in a few words. To say it easy, the green-blue curve shows Vasculoy, and this curve is highest, which is good. That means gives the best corrosion resistance. The interesting characteristic values for the corrosion are protection potential, breakdown potential, and passive range, with the protection potential as most important. The value for the protection potential reflects the healing effect of the surface if the surface of the stent is scratched, for example, by a guide wire, or if two stents are in contact in a bifurcation vessel situation. With a high protection potential, the stent surface heals faster and regains corrosion resistance. And you can see that Vasculoy has by far the highest protection potential of here more than 1000 millivolt, higher than stainless steel, and far better than L605. So the take-home message is Vasculoy has the best corrosion resistance of all stent materials. Of course, also the biocompatibility of Vasculoy has been tested accordingly to the ISO standard 10993. The results are as follows. Vasculoy has no proliferation inhibition, no hemolytic effects, no activation of the coagulation system, no quantifiable leachable substances, and again, no detectable substances. So Vasculoy has a perfect biocompatibility with no compromises. The magnetic resonance imaging compatibility is another important characteristic of stent materials. Stents should not limit MRI screenings of patients. Here in the right picture, you can see the investigations under high magnetic resonance fields. For the comparison again, identical stents had been manufactured, but with different materials, 316L, L605, and Vasculoy. The results are sometimes slightly better for Vasculoy, sometimes better for L605. I guess, or we guess, it is in the range of the accuracy of the measurements. But they are always better than stainless steel. So the take-home message is the results of Vasculoy are superior to stainless steel and comparable to L605. Radiopacity. Cardiologists desire visibility of the stent in angiograms during implantation, but also on follow-up situation. As the density of Vasculoy is similar to 316L, the visibility is the same. It is hard to see the stents, especially if the struts are very thin. This is shown here. We recommend radiopaque markers. Best would be 2 on each side of the stent. These markers ensure a good visibility without artifacts and with no compromises to the stent materials. I hope you can see it on your screen in your computer, where you hear the markers of the Vasculoy stent. Here I want to make a short excursion to the platinum chromium stents, which is the stent material with the highest material density and therefore has a better visibility. But on the other hand, it has a few disadvantages, which are due to the platinum content, very high material cost, lower material strength, less corrosion resistance, and especially artifacts in high-resolution angiograms. If the material, or any material which shows a good radiopacity, you cannot look into the stent. The view is blocked by the material, so by the struts of the stent. So we recommend, if you're looking for a good visibility, for radiopaque markers. Finally, I want to show the comparison of the 3 materials, 316L, L605, and Vasculoy in one slide. So we have the mechanical properties. Vasculoy has similar or equal strength like L605, but better, far better than stainless steel. For plasticity or strain, Vasculoy is again equal to L605, better than stainless steel. Corrosion resistance. Vasculoy is better than stainless steel, far better than L605. Biocompatibility. Vasculoy is the only nickel-free stent material. MRI compatibility. Vasculoy is similar to L605 and better than stainless steel. And for radiopacity, markers enable good visibility. So the take-home message is Vasculoy is the best material for stents and other implants and the only chance for nickel allergic patients. With all this information, if a medical company decides to develop a Vasculoy stent, the roadmap is as shown here. First of all, MeKo will support the development. Customers could send us a design which most probably can be identical to an existing L605 stent, so no changes have to be done. MeKo manufactures the samples and prototypes. The costs are reasonable. They will be below 2,000 euro. Then the initial testing of Vasculoy stents have to be done by the customer. We expect results that the results will be equivalent to the existing L605 stent. If the customer decides for Vasculoy stent registration, MeKo will assist. All necessary biocompatibility data concerning the material will be provided by MeKo for free. So we feel that we are responsible for the material and will deliver all necessary material data. And we can support with a lot of documentation, with a lot of nickel allergy literature. If serial production starts, MeKo will manufacture these stents for prices similar to L605. Here in this slide, we have just a short list of literature. You can make a screenshot here or later download the webinar and see the list of literature. If necessary, we have far more information. Finally, at the end of my talk, I want to finish my presentation with one question. If two stents are on the table, the design and the mechanical properties are identical, one with nickel, the other without. Which stent will you take? Thank you for your audience. I give back the microphone to Laura.
So now I would like to thank Clemens Meyer-Kobbe for his time to share his expertise with us and everyone else for joining us today. The video will be available on our homepage later on and also on YouTube. We hope to hear from you soon again and have a great day.
Goodbye.